Okay, so I'm going to make a couple of videos for section 6.2 in your book, and essentially the idea is, as of right now, if I draw a right triangle like this, and if I give you a side and this angle, you can find everything else in that triangle. You can solve the triangle. You can find this side, and that side, just using your trig ratios. We did that in section 6.1. The problem is that works because we know our trig ratios and right triangles work really nicely. And the question is, what happens if we want to solve a triangle that isn't a right triangle? So suppose we have a triangle that looks like this. Can I solve that if it's not a right triangle anymore? And there actually is a trick to do it, and I'm just going to quickly prove the trick algebraically because it's not too hard, and it's beneficial to understand how to do it so you can do it on your own. And the idea is, well, in your book, you use capital letters for angles, so we'll say that's angle A, that's angle B, and that's angle C. And then the sides opposite them, if that's A, this side is lowercase a, this side's lowercase b, the bottom is lowercase c. And now I want to somehow find a way to relate the angles and the sides together, even though it's not a right triangle. So what I can do is go back to the geometry I know and draw a perpendicular bisector right here. All of you remember that from the geometry. And then that becomes a right angle. And this thing, I can just call it the height. That's usually what we call it in a triangle, h. Well, now I formed a right triangle, and I actually formed two right triangles. So create your trig ratios for both of these triangles. And say, for A right there, I'm going to incorporate the h. So we will say that, well, what incorporates this angle, this h, and that b? That's sine. So sine of A equals opposite, which is h, over hypotenuse b. And then just algebraically, I'm going to multiply the b over, just so I get an equation for h. So I get h equals b sine A. But then over here on this side, I'm going to do the same thing with b, h, and a. So I can get sine of angle b equals the opposite h over the hypotenuse a. And again, just like over there, I'm going to multiply the a over to get an equation for h. So I get h equals a sine b. But now, algebraically, I have h equals b sine a and h equals a sine b. Since they're both equal to h, they're equal to each other. And then I can write b sine a equals a sine b. And this actually works completely fine. In my seated class, some people were saying, can we just leave it like this? You can, but generally we don't. What we do is, I'm going to divide the lowercase b to this side and the lowercase a to that side. When you just do that, you end up getting sine of a over a equals sine of b over b. And essentially now, I've created a proportion. The ratio of the sine of an angle to its included side, or to its opposite side, is equal to the sine of an angle and its opposite side. And I've kind of completely eliminated h, but this gives me a nice little trick that I can use to actually use angles and sides of a triangle to find other angles and sides of a triangle, which is my goal when I'm trying to solve a triangle. I'm kind of leaving it off here, but you could have actually drawn your perpendicular bisector from any angle that you wanted, and you can kind of keep doing this same trick over and over. And as it turns out, both of those ratios are also equal to sine c over c. Exact same principle applies. I'm not going to draw it all out. This is what's called the law of sines, because it uses the sine, and it just allows us to solve triangles that are not right triangles. One question I had in my seated class yesterday was, does the law of sines work for a right triangle? Test it and see. It should. Do the algebra and see if it actually works. But We just want to use this rule right here in order to solve a few triangles. And I have a few problems I wanted to look at to kind of cover different issues that can arise. So first off, we're going to say this. Suppose I have a triangle where angle A equals 57 degrees, side A equals 62, and side B equals 50. Solve the triangle. Just draw a triangle. It does not have to be perfect. You don't have to pull out a protractor or anything. I really just need a triangle. And now label it. Let's see. We'll call this A like we did before, so that's 57 degrees. That makes this side A, which is 62. We called this one B before on the right, which means this is B, so that's side B, which is 50. That makes this capital C, and that lowercase c. And now I want to solve the triangle. I'm going to have to grab my calculator so we can do these calculations out. And let's see. Well, in order for the law of sines to work, I need at least one ratio of an angle to its side. And in this case, I have that for A. This angle, angle A, to side A. As long as I have that, then I can make the law of sines work. So let's see. I have this. And then I have this side, so I'm going to start by finding that angle. So set up my ratio. Sine of 57 degrees over 62 equals sine of B over 50. Now, solve for sine of B. So multiply the 50 over. And you get 50 sine 57 degrees over 62 equals sine B. And now to get B out, just multiply all this out, throw it into your calculator, and take the sine inverse, and see what we get for angle B. All of you can hit the buttons on the calculator, so I'm just going to throw it into mine and see what we get. 50 sine 57 divided by 62. Okay, and you get that. Just to write it out so all of you can check yourselves, sine B equals 0.676. Now take the sine inverse. (42.5). So B equals 42.5 degrees. There is one possible problem that can arise that we'll see. Right now, we're going to say that B equals 42.5 degrees. But if you think about the unit circle, how many angles will have a sine of 0.676? There's actually two of them. One in the first quadrant, one in the second quadrant, which means there's two potential angles that side B could be. So you have to check it. And all you say is, well, let's see, in terms of the unit circle, either B is 42.5, that would be my reference angle, 42.5, that's first quadrant, or I'd be over here in the third quadrant. This would be 42.5, so what angle is that? Just subtract from 180. And let's see, we get 180 minus 42.5, 10 minus 5 is 5, 9 minus 2 is 7, 7 minus 4 is 3, 137.5 degrees. And then you're left with the question, which of those is correct? 42.5 certainly seems to work. Does 137.5 work? It could. It might. All you have to do to check, take this angle, plug it in with the angle you already know. If you end up with something less than 180 degrees, then it's a possibility, because all you need is for all three angles to add up to 180. So if these two add up to something less than 180, then it allows a third value for angle C, and you can get a triangle. If this angle and this angle add up to more than 180, then it clearly can't be a triangle because the sum of the angles has to be 180. So all you have to do is check when you're doing this out. And in this case, 137 and 57 is more than 180, which just tells me this angle doesn't work, and the only one that will give me a triangle is 42.5 degrees. If that's a little confusing, we're going to go over one or two more examples. I might have to make another video of it, where you'll get different possibilities, and maybe you'll get two solutions, which occurs sometimes, just so we can see it in action. But now, just using this, we say B is 42.5 degrees. Now all I need is C and C. But if I know these two angles, then I know the third angle because they have to add up to 180. So let's see. 57 plus 42.5, that's 99.5 degrees. Which means this one, all of you can do the subtraction, is 80.5 degrees. Now, since I know this angle and I want to find this side, I can just apply the law of sines again. So let's see, we're going to run out of room, so we'll just go right over here. And we can just do the same thing. Sine of 57 degrees over 62 equals sine of 80.5 degrees all over C. Now, just make sure you do your algebra correctly, and we'll work this one up just so you can see it. Multiply the C and multiply the 62. So you'll get sine 57 degrees times C equals 62 sine of 80.5 degrees. Now, divide the sine 57. So you get C equals 62 times sine of 80.5 all over sine of 57. Now, throw it into your calculator and get an answer. So really quickly, let's see. And I get 72.9. And apparently C is 72.9. And now we've completely solved the triangle. I'll erase this just so it's out of the way. And now we have all the sides and all the angles. One last thing I'll mention. You should be able to look at your triangle and your solutions once you have them and see that what you got is correct. And what I mean is, the angles have to add up to 180. They do. We made sure of that. The bigger the angle, the bigger the side. Meaning, this is the smallest angle, 42.5. Its side is 50. The next angle is 57. The next bigger angle, it opens to the side of 62. The biggest angle is 80. It opens to the biggest side, 72. So it's logical. It makes sense. Just check things like that and see that your triangles make sense. The biggest mistake you're going to make, since all of you know how to solve proportions and cross multiply, the biggest mistake you'll make is either a random algebra mistake when cross multiplying or hitting a wrong button on your calculator. One of the ways to check that, just look at your triangle and see, does my answer make sense? If it does, probably good. If not, go back and check all your work to make sure you didn't make a simple mistake. Like I said, I'm going to make another video looking at a couple other possibilities that will arise here, and then we'll kind of go from there and look at a few more applications.